Good morning. My name is Junqiu Liu. I'm a PhD student in the Laboratory of Photonics and Quantum Measurement, led by Professor Tobias Kippenbeck at EPFL. Today, I'm very honored to give the last talk in this section. In this talk, I'll present our recent work on monolithic piezoelectric control of soliton microcombs, which combines integrated photonics with MEMS technology. This work was performed in collaboration with Sunil Bab's group at Purdue University. As you may learn already from previous talks in this section, the dissipative Kerr soliton is a traveling pulse circulating in an optical microresonator. Analytically, the nonlinear driven system can be described by the Luggiato-Lefebvre equation, which describes the interplay between dispersion, nonlinearity, loss, and gain. Under particular situations, when dispersion balances the nonlinearity and gain compensate the loss, the solution is a traveling pulse with a CW background, and this is the soliton solution. The soliton has a smooth spectral envelope in the set shape and ultra-narrow beam node and high coherence. So far, Microcomb has been demonstrated in a wide variety of material platforms, such as silicon nitride, silica, fluoride crystals such as calcium fluoride and magnesium fluoride, aluminum nitride, lithium niobate, tantalum pentoxide, fibroferrule, Hydex, aluminum gallium arsenide, and gallium phosphide. For our research, we built a photonic integrated circuit with silicon nitride. Silicon nitride has several advantages. It has a wide transparency window from visible to mid-IR. It has a high Kerr nonlinearity, almost an order of magnitude higher than silicon. It has a weak Raman and brane gain. It has a large band gap of 5 electron volts, which makes silicon nitride immune from 2-photon absorption at telecom band. The fabrication process is CMOS compatible. Therefore, we can build robust coupling between the bus waveguide and the ring resonator. By changing the geometry of the waveguide, we can engineer the dispersion and achieve broadband microcomb spectrum. In this talk, I will show a silicon nitride microresonator of Q more than 30 million with enormous group loss dispersion. This corresponds to a linear propagation loss of 1 dB per meter due to our optimized Photonic Damascene process. And then I will show the monolithically integrated aluminum nitride piezoelectric modulators on silicon nitride photonic circuits. By changing the voltage, we are allowed to control the soliton initiation and realize soliton stabilization. Also, we can do high-speed integrated soliton locking. Then we use this new capability to demonstrate a hybrid soliton-based massive parallel LIDAR engine. To fabricate silicon nitride photonic integrated circuit, we developed and optimized the Photonic Damascene process over the past few years. In this process, we use a clean wafer substrate and perform deep UV step lithography on the wafer. And then we transfer the pattern from the photoresist mask to the substrate. We further anneal the substrate to smooth out the sidewall roughness. And then we deposit silicon nitride on top of the patterned preform. A planarization is needed to remove the excess silicon nitride. And in the end, we put top cladding, annealing, and then separate the chips. This process was inspired by the Cooper dual Damascene process used for Cooper interconnect circuit. An advantage of this process is that we can pattern the feedback pattern to release high tensile stress of silicon nitride to prevent the crack formation. Center to photonics is the waveguide loss. So far, The lowest waveguide loss has been achieved only in fiber, which is 0.2 dB per kilometers, and which makes the global fiber communication possible, thanks to Charles Kao. In integrated photonics, for industrial application, the optical losses is typically at the order of 1 dB per centimeters, where our integrated photonics based on silicon nitride has the record value of 0.01 dB per centimeter, 2 orders of magnitude lower than this value. To achieve such low loss, we have been developed and optimized our Photonic Damascene process for several years. This chart shows that our silicon nitride microresonators Q improvement corresponding to loss reduction in comparison with the work from other groups. Today, we are able to routinely achieve more than 10 million quality factors of optical microresonators, which correspond to light propagation distance of a meter in nanophotonic integrated waveguide before the photon gets lost. This is only possible as a result of the entire silicon nitride community after a decade effort on the fabrication process. To fully characterize the loss of our integrated microresonators, we measure the resonance line width of many resonances, more than 10,000, and analyze their statistical distribution. As shown here, in 40 GHz FSR microresonator, we have achieved 6.5 MHz intrinsic line width as the most probable value, which corresponds to an intrinsic Q factor of 30 million. The 30 million Q value corresponds to 1 dB per meter loss. We also study the yield of our fabrication. The measured loss of each sample at a different location on a 4-inch wafer is measured. As you can see here, in most of the locations, 6.5 MHz line width is maintained. This study proves that our fabrication process is wafer scale, reliable, high yield, and reproducible. We can deliver more than 160 working chips on a 4-inch wafer, which requires only 4 weeks of fabrication time. Recently, we further perform experiment and simulation in order to understand that among 6.5 MHz line width, how much is contributed by the scattering losses and how much is from thermal absorption losses. The method we use is to modulate the intercavity power and measure the resonance frequency shift in responding to such intercavity power modulation. We have observed such response curve which present 2 cutoff frequencies. The cutoff frequency at 14 kHz is the thermal cutoff, limited by thermal conductivity and capacity of silicon nitride and silicon dioxide. The cutoff frequency at 6 MHz is the cavity line width cutoff. By fitting the response via thermal heating simulation of our silicon nitride waveguide, we can calculate the temperature change caused by the thermal absorption. In such a way, the thermal absorption losses can be extracted from fitting the measured response with theoretical curve. Here shows the statistics of many measured resonance and extracted thermal absorption losses. We identify an average 0.2 MHz thermal absorption losses within 6.5 MHz total loss. Higher absorption losses are found around 15-20 nanometer, which correspond to hydrogen absorption in silicon nitride. This average 0.2 MHz indicate that in the ideal case, that the loss is only limited by the thermal absorption, the Q value of silicon nitride can reach 1 billion. As silicon nitride is an insulator, The implementation of optical modulation on silicon nitride is challenging and typically require other material to assist. Electro-optical modulation using porous material can be realized by heterogeneous integration on silicon nitride. The integrated EOM feature high speed above 10 GHz and large tuning efficiency of 7 picometers per volt. However, the disadvantage of this scheme is that it's only limited to EO materials by heterogeneous integration or PZT via softgel. During CLEO, my colleague will also present our recent progress on hybrid silicon nitride lithium niobate integrated platform for EO conversion. The second scheme relies on graphene modulators. This scheme also has high speed, above 10 GHz. The graphene layer can be grown or transferred to silicon nitride photonic integrated circuits via multiple schemes. The disadvantages are, first, the modulation is electro-absorptive, so the loss of the device is modulated. It requires weak optical confinement such that part of the optical mode interact with the graphene layers. The third scheme relies on thermal heaters, which can work on a variety of materials. It enables large tuning range of 1 microresonator FSR. However, heaters are slow, with actuation bandwidth typically between 1 kHz to 10 kHz. Also, it continuously consumes high power around 100 milliwatts. Third, it enables only one directional tuning, as heating the chip is much easier than cooling the chip with current. Recently, it has been shown that piezoelectric material are also useful to make optical modulators. The principle is based on geometry variation or the stress optical effects, and the latter is more often explored. By applying stress on the material, the refractive index changes in response to the applied stress. Piezoelectric modulators are high speed up to several gigahertz and can be applied on any material of platform, not only silicon nitride. As piezoelectric, the modulator are capacitive, thus they consume low power. The disadvantages are, first, this scheme is limited to only piezoelectric materials as modulators, which include PZT or aluminum nitride. The geometry variation requires suspended structure. Also, if you use ferroelectric PZT, which has low breakdown voltage and hysteresis of the tuning, the non-ferroelectric aluminum nitride have very low tuning efficiency, which is about 0.3 picometer per volt. The non-ferroelectric aluminum nitride modulator is the material that we choose in our work. As I mentioned very early, aluminum nitride integrated waveguide can also be used for microcomb generation. In the MEMS community, aluminum nitride is one of the most widely used material to build modulators and filters using bulk acoustic wave. When applying an AC driving on an aluminum nitride thin film, the top and bottom interface serve as acoustic mirror due to the acoustic impedance mismatch between different materials. In this case, acoustic standing wave can form, which is commonly referred as bulk acoustic wave. The aluminum nitride thin film bulk acoustic resonator can be fabricated with CMOS compatible fabrication process. And the aluminum nitride can be deposited via physical vapor deposition at a low temperature, about 350 degrees. Aluminum nitride is polycrystalline and non-ferroelectric, and the melting temperature of aluminum nitride is higher than 2,200 degrees, which makes aluminum nitride suitable for extreme environment. The speed of sound in aluminum nitride is about 8,000 meters per second. Therefore, if you have micrometer film thickness, you can get a gigahertz acoustic frequency. The power conversion efficiency from electric to acoustic is about 6% at a typical Q value, mechanical Q value of few thousands. The frequency response of the aluminum nitride bulk acoustic resonator is the equivalent to the BVD model of an electronic circuit with inductor, resistor, and capacitor. When sweeping the AC driving frequency of the aluminum nitride bulk acoustic resonator, there are resonances and anti-resonances observed. The resonance has a high admittance and a low impedance, which correspond to a closed circuit. The anti-resonance has a low admittance and high impedance, which correspond to an open circuit. On the anti-resonance, the energy is dissipated in the bulk acoustic resonator. The frequency separation is determined by the K-square, which is the power conversion efficiency, times the center frequency. By combining several aluminum nitride bulk acoustic resonator, one can build an RF bandpass filter. It is nowadays a successful technology. Tens of units of aluminum nitride RF filters are used in modern cell phones. Angelen and Avago today can produce billions units per year to the market. In our work, we build piezoelectric aluminum nitride modulator on our Damascene ultra-low loss silicon nitride photonic circuit. On left is the fabrication process flow. The optical micrograph shows the disc-shaped aluminum nitride modulator covering the silicon nitride waveguide. The SEM image shows the sample cross-section. As we use thick silicon dioxide between the silicon nitride waveguide and the aluminum nitride modulators, the optical mode is far away from the metal, which maintains the low loss in silicon nitride waveguide and keeps a high microresonance Q of 20 million. This slide shows how the device looks like. When applying an AC driving voltage on the aluminum nitride, the stress effect or the bulk acoustic wave can be induced, which modulate the incident photon. If soliton is generated in the microresonators, all the soliton comb lines are modulated at the same speed. With this new capability, we can control and modulate the soliton state by external RF driving. We first characterize the sample. On left, it shows the resonance tuning versus the voltage applied. The linear tuning efficiency is 15.7 MHz per volt. A very weak hysteresis is observed, showing that our aluminum nitride is high quality polycrystalline. On right shows the microresonance Q and the dispersion with different applied voltages. As seen, there's no Q degradation and no dispersion change. With this new capability, we show here voltage-controlled soliton initiation and switching. Here, we use a laser with a fixed frequency and apply the voltage on the aluminum nitride actuators to tune the resonance to the laser. When the resonance scans across the laser, a soliton step is observed. By applying different voltage, we can initiate the soliton and control the soliton detuning values, which in turn change the soliton bandwidth. This also allows us to stabilize the soliton detuning over a long term via active feedback. Note that the power consumption here is only 300 nanowatt, caused by 2 nanoamp leakage current. We further characterize the electro-to-optical transduction using a setup shown here. A vector network analyzer applies the sweeping frequency driving on the aluminum nitride actuator. The laser is tuned the slope of the resonance. By modulating the aluminum nitride, the transmission changes correspondingly, thus allows us to measure the electro-to-optical transduction as shown here. There are many peaks observed which have the profile of acoustic resonances as I showed in the previous slide. The peak of several hundred kilohertz are contour mode. These are simulated contour modes based on the chip size of 5 by 5 millimeters. The vibration is in the chip plane, corresponding to millimeter acoustic wavelengths. The peak around 70 MHz and the multiple of 70 MHz are high overtone bulk acoustic modes, the HBAR modes. HBAR modes are acoustic standing wave in the material stack with micrometer acoustic wavelengths. Our chip thickness is 230 micron, which corresponds to 17 MHz HBAR mode spacing. Next, we perform active stabilization of soliton repetition rate using the aluminum nitride actuation. As our soliton has 200 GHz repetition rate, which is not electronically detectable, we instead generate an EO frequency comb with 14 GHz line spacing and lock the 200 GHz soliton microcomb line spacing to the multiple of EO comb line spacing. We lock the -1 soliton comb line to the -13 EO comb line and detect the bit node between the +1 soliton comb line to the +13 EO comb line. Note that both combs are generated with the same pump, so their zeroth order lines are the same. Here we show the bit node signal before and after locking, and the phase noise of the bit frequency. The phase noise in the unlocked and the locked state merge at 0.6 MHz, which determines the locking bandwidth of our device. With the new capability of integrated microcomb modulation, we demonstrate a new application using solitons for frequency modulated continuous wave LIDAR. The FMCW LIDAR sends a frequency chirped CW laser to a moving object and detect the reflected signal from the object. The heterodyne bit signal between the initial signal and detected signal allows to recover the profile of detected signal. The time delay corresponds to the time of flight and allows to calculate the distance between the laser and the object. The frequency shift is due to the Doppler effect, which allows to calculate the speed of a moving object. Using soliton microcomb, we can build a massive parallel FMCW LIDAR. By chirping only the pump laser, the frequency chirp is simultaneously transferred to all comb lines. By dispersing each optical channel which manifests as an independent FMCW LIDAR, massive parallel data acquisition can be realized. There are two schemes to implement Soliton-based FMCW LIDAR. The first scheme uses a fixed microresonator resonance and a modulating CW pump within the soliton existing range. This method manifests as a soliton detuning scheme. As a result of the variant soliton detuning, the soliton spectrum changes correspondingly, as well as the soliton pulse power. In addition, the frequency excursion cannot exceed the soliton existing range. Furthermore, when changing the soliton detuning value, the soliton-induced Raman cell frequency shift also changed the soliton repetition rate. In the end, the frequency excursion of each comb line is not equal, as shown here, which results from the change in the soliton repetition rate. The second scheme is feed-forward scanning, which is a better solution. In this case, the laser and the resonance are modulated synchronously, such that the soliton detuning is a constant. As a result, the soliton spectrum and the pulse power are constant during the scanning. In addition, the frequency excursion is no longer limited by the soliton existing range, and it can go significantly beyond. Furthermore, free from the Raman cell frequency shift, the soliton repetition rate is constant, and each comb line has the same frequency excursion, as shown here. This scanning scheme is superior as it manifests as a scanning of the carrier envelope frequency of the microcomb, the FCEO, while the comb repetition rate is unchanged. Furthermore, by modulating the microresonator at an HBAR frequency, we could significantly increase the modulation efficiency. The AC tuning efficiency at HBAR frequency is 290 MHz per volt, but at the DC tuning speed, it is only 15.7 MHz per volt, more than an order of magnitude slower. We can easily reach 1.5 GHz frequency excursion using only 7.5 volt driving voltage. This is equivalent to 58 petahertz per second tuning speed. The driving voltage reduction with the HBAR mode could allow us using a CMOS electronic circuit to drive the soliton photonic circuit. In the last, I will show you the final proof of concept demonstration of ranging experiment using our Soliton-based FMCW LIDAR. We use it to map the profile of an EPFL logo. This is the data of the ranging results. The distance resolution is better than 5 centimeters that can be further optimized. This is the last slide of my talk. For more information, please refer to these 3 references. Thank you very much.